Hello, I'm Adarsh Narayanan.
And I'm Tanishka Dhake.
This is our AE1601 glider final project report.
So first off, our design process. The requirements slash measures of success for this project were that the glider must go 20 feet. It must fit in a box that is 16 inches by 16 inches. The maximum wing loading must be 0 0.5 grams per centimeter squared. The minimum aspect ratio is 5, and the final glider must be more than 50% balsa wood by weight. So we were faced with multiple design choices as we went about this process. For the materials, balsa wood was provided, so that was what we automatically used for the main body of the glider. Additionally, for the mass, clay was provided, so that was what we ended up using. The wing shape, we considered several different platform shapes, such as rectangular wings, tapered wings, elliptical wings, etc. But through our research, we found that an elliptical wing would give us the best uh, uh, lift to drag ratio. The wing placement angle, we experimented with this a lot um as we went through the different iterations of our design. We adjusted how far it was from the front of the plane and we adjusted its angle of attack. We ultimately found that having a zero angle of attack on the plane itself and having the wing be placed about 5 inches from the front was the best for our glider. A dihedral was considered, but it would have been difficult to build and the flight was stable without it, so we opted not to include that in our final glider design. For the tail configuration and angle, through our research and experimentation, we ended up choosing a conventional inverted T design, and we chose to keep the angle at 0 because through our experimenting with different angles, that was what performed the best. Adhesives, we used super glue because it was provided and it also dried faster, making iterations easier than if we had used something like wood glue. Sizing of the glider was limited by the 16-inch by 16-inch requirement, so we just chose the sizing of the wing and fuselage that would maximize the space that was given. So we researched a lot about wing shapes, tail shapes, dihedral angles, and winglets. The wing shapes, we found that elliptical wings would give us the best ratio, so we chose that. The tail shapes we used an inverted T shape. Dihedral angles, we considered the dihedral and we would have added it if our plane wasn't doing that well without it, but we did have a relatively stable flight without a dihedral, so we opted not to include it. Winglets, a similar story. We would have added it if our plane was not doing that well without it, but it was doing perfectly fine, so we opted not to include them. For our design choices, we ultimately had a wingspan of 16 inches. We had a straight, uh, a simple elliptical wing and also an elliptical tail. The wing area total was 24.51 square inches, and so that resulted in our aspect ratio being 10.45, which is greater than the minimum aspect ratio given earlier. The glider was manually balanced for longitudinal stability with each iteration, and the center of gravity for our final iteration was roughly even with the quarter cord. We had 4 grams of clay added to the front for balancing. So to calculate the lift and drag coefficients, we first calculated the velocity from our final flight to be 6.858 meters per second. The platform area is 0.0158 meters squared. The density at around 320 meters elevation, which is what Atlanta is 1.1 kilograms per meter cubed for the air. The mass of the glider was 0.0143 kilograms, and the distance it was able to travel was about 13.7 meters, and it was thrown from a height of about 1.82 meters. So this resulted in our lift to drag ratio being 7.5. Our coefficient of lift, based on the formula given to us in class, was 0.1, sorry, 0.84. And using the lift to drag ratio and the coefficient of lift that we calculated, and the formula given, we were able to calculate that the coefficient of drag was 0.112.
So for our design iterations, we experimented with different placements of the wings. We tested different weights for the mass, and we tried to sand the wings to create an airfoil. But we found out when we sanded the wings, it wasn't even enough. So we were seeing some drift when we were throwing the plane. So for our final design, we decided to opt out of the the airfoil. So we just kept the original design without the airfoil. And we had an aspect ratio of 10.45, as said before, and our wing loading was 0.09 grams per centimeter squared, which was more than 0.05. Also, our plane fit between the 16-inch by 16-inch requirement. So for our first iteration, we had the airfoil of the wing. It was 15.3 grams, and we used rubber bands instead of glue. Also, we had a mass of about 4 grams. That plane traveled about 30 feet. So for our final iteration, we didn't use the airfoil. We had 14.3 grams, and we had 4 grams of clay. So it was more than half fully balsa wood. We also glued the parts, and it went around 45 feet. So in summary, we designed, built, and flight tested a small balsa wood glider using iterative design, trimming, and weight adjustments to improve stability and lift. We also used elliptical planforms for the wing and rudder to reduce drag and smooth airflow. And we finally launched the glider and reached the best range of 45 feet, which was more than double the 20 feet requirement. And these are citations.